Cool. Sorry for the delay. Now, what do I want to do today? Good question of the day. So we are essentially done, I think, with what I really call the core lectures. And I wanted to just get a little bit on the project. And as you will see, it's not too complicated. I don't want to make it too complicated this first round, since I don't know how well things work. We've never done that in this form. First of all of you have, just almost all of you most likely have by now, that simulator running in some form. And the homework assignment gets you going essentially on planning a trajectory and following a trajectory. And that's kind of one core component which we need. The other core component which we need is that we can do something like inverse kinematics. So let's see what we have here after. Let's go to my little now. Where is the robot from the previous page? Oops, the wrong computer, which I'm fumbling around with. So fine, we have the now robot. And one thing which would be nice to accomplish is, it's really a simple project. Get this now to basically step with its feet such that you get all the weight on one foot and you can stand on one foot. Okay? This is essentially not a hugely complicated project, but it requires that you, well, you can do it in many ways. Let me just close it on here. But it requires that you essentially can plan a smooth trajectory to get on one foot and have some criteria on how to basically figure out what you're doing. So what do you need? And that was actually part of homework number 2. You need to reason a little bit about the center of mass. Since when does a robot actually balance? It's very simple. So the center of mass, which is usually somewhere shown with this kind of silly circle. If the center of mass is between the 2 feet, basically, if you project it on the horizontal plane on which you're standing here, and you put your 1 foot up, you fall over. What you need to do is you need to get the center of mass over so that it, what is called the support polygon of 1 foot. So it's make 1 foot of the now roughly look like this. And so you want ideally the center of mass to be smack in the middle. So we have essentially a center of mass planning and execution problem to make this work. And if you look at the simulators, let me see whether I can get the simulator up. How do I do this in an intelligent way? Okay. So let's see how far this is going to work. Does this work? No. Okay. Okay, I got it. It's just the wrong window, which I'm sharing, which is boring. Yep, here it is. So this is what the simulator looks like, and there should be somewhere a red ball, at least, if I correctly remember that. Does it have a red ball? If it doesn't, I have to fix that. Which shows the center of mass. So actually, I thought there is one, but I'm not sure anymore. Let's see. Oh, I know. Yeah, makes total sense. Thing is up in the air. Boing. Okay, here is the red ball. So what did I just do? But I will send you instructions on that as well. On the now task window, right now I did something which is called freeze base. That basically makes the thing fall off and it's basically free and standing. And then the moment you have that, you get actually the center of mass here projected onto the standing plane. And that is kind of your indicator where you are. You essentially need to get this red thing into 1 foot so you can stand on 1 foot. And if you can do this, then you can actually do fun things. You can actually do it from 1 foot and then you do it to the other foot. A little bit tricky, so you cannot basically move, if you want to step from 1 foot to the other foot back and forth, you have to do this in such a way that you don't fall over in between. So it might actually become a more complex behavior where you first basically have both feet on the ground, then you shift somehow your butt over so that your center of mass is on 1 foot, then you can lift up one leg, then you can put the leg back down, shift to the other foot, get the other one up. If you start shifting while the other foot is in the air, you may fall over. So in essence, what you need is a simple way of just basically creating a small step of sequential behaviors, which first gets the foot on the center of gravity on one component, on 1 foot, leg up, leg down, and then shift it over to the other side. But it's just nice if you can at least get it balanced on 1 foot. And we'll see how hard this is. So what does it take to do that? Well, you will get from us the center of mass position. So of center of mass in X, Y, and Z. And I will tell you which variables this is in an email. So it's not very hard. So in our world, the vertical axis is going up. This is Z. So we only care about the XY plane. That means the component in the XY plane. And now we just have to control it over. Now, it turns out what you did in homework assignment 2 is literally that. So you were actually controlling the center of mass of the robot with inverse kinematics, if you recall that. So how does that work? If you recall, in this homework, you had a multi-folding arm. We made some very simplifying assumptions where the center of mass is. We put them actually in the end position. It's not really where it is in fact for robots. Usually it's somewhere in there. These are the center of masses of every link that together gives some center of mass of the entire robot. And then you were controlling this with inverse kinematics in this particular case to create something like this. Now all what you got to do now is do literally the same thing in a slightly more complicated system. And instead of doing the sinusoidal motion, you just do a movement from left to right. That is basically using actually the minimum jerk trajectory, for instance, which you are doing now in homework number 3. That's a very nice and smooth way of doing it. You don't want to just bump it over, it will fall over immediately if you see that. So this is kind of the nice way of doing it. So you basically do an inverse kinematics on the center of mass. And they move the center of mass to a target position. And the target position is where the foot is. How do you figure out where the foot is? Well, you can but we have some variables which are called card state. Again, I'll send you an email about these things as well. And card state is basically the Cartesian state of all end effectors of the robot. The robot has 2 arms and 2 feet. So let's see what that is. If I go to the appropriate window, hopefully I get the right one. Nah, of course not. Still not. Trial and error. This one. Ugh. This one. Yes. Okay, so this is this task server window which you've seen before. Let me see if I can make this a little bit bigger. No, I can't. I can. Oh. And there's some command which is called cwhere, if I do this correct, and it gives you the positions of all n effectors, in particular the right foot and left foot. The right foot is currently at x equals 0.05, y essentially 0, z minus 0.4. The floor is currently at minus 0.4 meters high. That's it. It's just how we define the floor. You get the same for the left foot. And so from that, you can actually read the position which you need and say, okay, now I basically want my center of mass to go to this x and y position initially. And then later on, I want to make my center of mass to go to the other x and y position. The only difference here is the negative sign. So this is plus about 5 centimeters. This is about negative 5 centimeters. Okay, so that's the only difference. So you get this target for the COM automatically from knowing where the robot is currently standing. So where's my pen? So we can get this from the variable in C programming, the variable card state. It's indexed by right foot and left foot. And there's also a card state of the left foot. And these structures have a variable x, and then they can be indexed in a minute. Wait here, not see this anymore. So they have an index of x, or they have an index of y, or an index of z. How you get the x, y, z coordinates where the foot is. So that's very easy to read out. So from this variable, you get the target for the COM, the center of mass. You get the center of mass position from us, which is literally calculated the same way as you had to do it in your homework assignment. You basically sum up the center of masses of all links divided by n. So the positions, of course, and you get the average of everybody. And then we have to create a way to get to this position. Now, there's multiple ways how you can do that. If you want to do it really nicely, you do an inverse kinematics approach. If you want to do it really crummily, you could actually figure out a posture. That means a set of joint angles. So we have all these joint angles in joint states. And we have joint desired state. These structures, this is the current value of the joints, and this is the desired one. You could, of course, try to figure out a particular set of joint desired states for all joint angles, which put your center of mass over a foot. Let me just get this picture back. Okay, which move the center of mass over there. So you could try this out by trial and error if you wanted to. And then you basically create a joint space target. And then you create a desired, a smooth trajectory how to get from your current position in joint space to that desired position in joint space. So this would be a complete joint space view of doing that. So how do you do things like that if you wanted to play with that? Let me do something different. Get rid of this. And that was a bad idea. Share my screen entirely. Okay. Make it a little bit bigger again. Hope this does something roughly. So in the task server window, there's a command which is called go. And if you can't read right now, unfortunately, so I just we just do the command go at the front, and then it asks you which degree of freedom you want to move, and you could simply say I want to move, let's see, degree of freedom number 4, which is, what is it, the right elbow. And now I can give the right elbow a new target value. If you could read that, you would see this, and I could say, okay, go to 1.3. And then you could see that the arm was twitching a little bit. Okay. That's also what happens if you stretch your arm out. Robot falls over. That's the interesting part of life. Okay. Reset, takes the robot back to where it was. So let's try this one more time. Make this actually bigger, it's more fun. Try another go. I can go 15. Which one is this? Some part of the leg, set that to 1. Didn't want that, just a second. Okay, that didn't work either. So, fine, you see a little bit that this is actually a system which falls over. But you can play with these joint angles and try to see whether you find a way how to adjust. That becomes essentially a manual, little bit hacking approach to find the right joint configuration which takes your center of mass over 1 foot. If you have it, you're fine. And you just have to basically, the next time, plan a movement how to get there, which is literally what you do in homework 3. It's a joint space movement with, for instance, a minimum jerk trajectory. It's a simple, smooth movement to do for all degrees. The nicer way, of course, is to do it with inverse kinematics. Now let's use the pins here. And if we do inverse kinematics, you need to look at homework 2, how the Simulink block was realized. So inverse kinematics means that you have as a control variable the target of the COM, let's call this target of the center of mass, that's your desired, minus your current position of the center of mass. So this is the difference, and you want to basically make the system move over there. So you can think of that as a x dot desired. You can put a little game in front of it to scale it down. And if you happen to have a target velocity desired, oh, this is actually, let's call this movement velocity. Not good, call it desired velocity. Okay? So if you have planned a trajectory for the center of mass, that means you're currently here, the center of mass is currently at a current position, you want to go there, you can plan a minimum jerk trajectory in 3 dimensions, x, y, and z, external space, to get there. And that would give you actually desired positions, desired velocities, and even desired accelerations over time. So the desired velocity you could use here. In the current position, actually you would in this case actually use the desired position in x to push you over there. You would be tracking a desired trajectory in center of mass space, which gets you from your current location to the target location. So at some time, let's say 1 second, the desired position in x would be the same as the target where you want to go. Okay, then you have this, and then you just have to run this through a Jacobian. Jacobian inverse times x dot desired, and this will give you some joint angle theta dot. And then you would have to basically integrate theta dots to figure out what your joint positions are. Theta equals theta dot times dt plus theta nu plus theta old, essentially. So that's an integrator which integrates up this trajectory. I'll give you a little bit more information in the handout for the project, which makes these things clear and reminds you of how this works. And then you have basically joint angle velocities, and you just have to basically put them into these current joint desired state variables, and we will move over. So you need to do homework 3 first to understand what I'm talking about. The moment you've done homework 3, that here will become very clear. The Jacobian, I will give you information where the Jacobian is. I will give you a skeleton file again, how to get programming, which has all the important variables pointed out to you. So that's something easy to get. Okay, if you can do that, then you can literally do proper tracking on the center of mass, move it over, and move it back. You can do other crazy things. You could move it up and down, or whatever you want. That's essentially it. So it is not a lot of complicated theory. It's all things you've done essentially in homework, particularly after you've done homework 3. It's not a lot of programming, and you just have to do it right. Otherwise, you will get this thing falling over all the time. And yeah, if you want to play around and do other things, then it's totally up to you. So the hope is that you get this going on the simulator first. And after you've got it going on the simulator, we'll try to get it on the real robots and see how well that works. Now, you will notice there is a big difference between the simulator and the real robots. These simulators are perfect physical systems. I should give you the picture here. They're perfect physical systems. That means we are simulating rigid body dynamics, and it behaves like a proper rigid body dynamic system with a certain amount of friction, certain inertial properties, no weird things. The real now has a huge amount of extra friction from gears and gearboxes and all kinds of things, so it will actually behave quite differently. And I think for the real now, for this task, which is actually just moving the center of mass, it's not a huge amount of movement. It's a very small movement. We will most likely not use any form of inverse dynamics, since I don't think the inverse dynamics does something useful on the now. It cannot be controlled with inverse dynamics in a reasonable way. So we'll just use PD control. So it makes it even easier. You'll see in the homework assignment 3 is in the bottom of the run part of the function, there is actually a call to the inverse dynamics, which makes it move more nicely. But we most likely leave that out for this project. Again, you will find this in the skeleton, which I'm going to send you in the next, whatever, 1 or 2 days, by tomorrow at the very latest. That you will have all the things in there, and I will put you a little remarks where you have to fill code in and what you will roughly have to do. So it will not be a complete recreation from scratch. Good, that's it. So it's not meant to be a huge amount of work, but it's meant to be a little bit of an experience with a real robot, hopefully, and give you a feel of what it actually takes to make something do what you want. Falling over, it will do by itself. You don't have to worry about that. Questions? Well, we gotta get it done somehow by the end of the month, or beginning of May. In the end, it's really the project is I wanted everybody does something. It's not that you fun. How can you fund it by not doing it at all? Otherwise, if it's a group work, it's something which should be fun for you guys, and hopefully we can really take either videos in the lab at some point that it worked, or you just show simulations that it worked. Basically, from every group, I want to see somehow that it did something. And maybe we do this in the second to last class, that would be the very end of April, that everybody just shows the simulation, and if it worked on the robot, a little video that it worked on the robot. Very short presentation. I think we all understand by now the theory how to do it. It's not very complicated at all. That's it. So I would like you guys to use really the coming time to work on homework and projects. So you need this homework 3 done as quickly as possible, so that then the project becomes a natural extension to that. That's actually what it's meant to be. And I think we use the classes primarily for question and answers. If nobody shows up, then we'll just work on it to get it done, so that we don't get into much time trouble. Now also post homework number 4, which is a small short homework. It's not going to be not much. More questions? Complete happiness? Okay, good. Then that's it for today. Just go homework number 3. Get it done so that you understand these variables. That you ask questions as soon as possible. You had enough trouble with installing of the current simulator. Hopefully it's now more smoothly running. Thank you. Yes.
To follow up on the problem the last week of the class on Tuesday.
Let me just finish this here.
Sure.